Okay, so I'm going to mute all the mics. Hold on. Okay, good. Okay, so you have that three-dimensional object. Okay, so you use method of cylindrical shells to find this value. Okay. So okay, so you know what? I'm just going to do this. This is what we'll do. We'll go back to the the word. Okay, here, the volume of the solid in the figure on whiteboard is obtained by rotating about the y-axis, region under the curve y equals f of x from A to B. Okay, that volume is B, which is equal to the definite integral B, which is equal to the definite integral from A to B of 2 pi x f of x dx, where 0 is less or equal to A and strictly less than B. Okay, the 2 pi x is like the circumference of the cylinder, and the f of x is like the height. Okay, so I'm going to go back to the picture, and I'm going to illustrate what's happening with this formula. So make sure to write this down, especially this whole theorem, right? So make sure you have this theorem. The volume of the solid in the figure on whiteboard is obtained by rotating about the y-axis, the region under the curve, y equals f of x, from A to B. So the volume sorry, just get rid of that is. So the volume of the solid in the figure on whiteboard obtained by rotating about the y-axis, the region of the curve, y equals f of x from A to B is that. Okay, so that's the theorem. Okay, so now if we go to whiteboard, so you see you have this curve y equals f of x from x equals A, which is 0, to x equals B, which is 2. And you rotate it about the y-axis. And so now you have this three-dimensional object that you get from this rotation, right? So I drew here was just the rotation of this point, rotation of this point, and the rotation of this point, right? Now, if you were to look at cylindrical shells, you would, in a sense, be, let's take a particular point. Let's take a point, let's take this point here, okay? Let's rotate this point here. So when you rotate this point here, you get, you get something like that, right? And this is where the point goes over here. Now, for cylindrical shells, you're just going to take the vertical part of it. Okay, you're just gonna. Okay, yes. Okay. Now there's going to be a little bit of a thickness to this cylindrical shell. Okay. Okay, so it's like if you took a vertical rectangle in this region and you rotate it around, then you would get this cylindrical shell. Okay, so you take this vertical rectangle here, right? That's part of the area under the curve y equals 2x squared minus x squared, or more generally just f. So you take this rectangle and then you rotate it around the y-axis, and so you get a cylinder, right? You get something that looks like this. Okay, but there's a little bit of a thickness to this. It's not two-dimensional, it's three-dimensional. And so you actually get, everything has a thickness to it because the original thing you rotated has a thickness to it. Okay, and so that's a cylinder. And so its volume, if you want to compute its volume, you could imagine that you took a scissor and you just cut it. So imagine if you want to know the surface area of this, so you want to know the volume of this cylinder. Let's say you just cut the cylinder right here, right, with just a vertical line, right? So you cut the cylinder like you had a scissor, but you cut a three-dimensional cylinder. And so then once you cut that, you open it up. So you open it up and you get, in a sense, a piece of paper with very thin thickness. Okay, so you make the cut on the green line, and what you get is you get a. I'm going to do this by hand. Okay, I can do it better by hand. Okay, so so then you get that, right, where this vertical thing that you cut, let's say that is this guy, is this side. Okay, this is where you made the cut, and then the other part, this part here, this top part, and this bottom part, that would be like here and here. So now if you wanted to find the volume of that, don't forget, right, this is three-dimensional. So there's a sort of thickness to this object. And so this thickness here, right? So it's kind of like that. Okay, so if you had the center, which is not part of the cylinder, but you look at the radius of this circle, then the circumference, the distance around the circle will be the circumference of a circle, which is 2 pi r. So the length of this red side is 2 pi r, right? So this would be 2 pi r here. That would be the length of the circle. After you make the cut, it's a straight line, right? And then this thing here, this was the height of the original cylinder. And so the height is there, okay? And then the thickness of it here, which you had here, this would be like the delta, this would be the delta x here. So you have a delta x here, which would be like the thickness of this rectangle. That would be the thickness of that. And so the volume of your cylinder, of your original cylinder, the amount of space it takes up in three-dimensional space, is 2 pi r h delta x. Okay? It's the circumference of the cylinder times the height of the cylinder, 2 pi r times h times delta x, which is thickness. So finding the three-dimensional volume of this rectangular, of this box, is the same as finding the volume of the cylinder. Okay, cutting it did not change its volume. Like cutting it and just opening it up did not change the amount of space it takes up.
Professor?
Yeah?
How is delta x and 2 pi r related?
So I think the useful way to answer that would be, let's say in this example, right? You have a graph here, and the height, right? So the height would obviously be the height of the graph, right? So h would be the height of f of x, right? H would be equal f of x. Okay. So I'm talking about easy things and then working my way. So h is f of x. Delta x would be the thickness of the cylinder, right? Delta x would be like the infinitesimal thickness of the cylinder, which when we use a definite integral, we would be using dx for, okay? So dx is going to be representing the delta x here. The 2 pi r is the is this thing. It's the circumference of that circle. Okay. So the 2 pi r here, right, is the circumference of the circle. In this problem, it's the circumference here, where the radius is the x coordinate. The radius is how far away, right, that point, any point on the circle is, the distance from that to the y-axis, right? It would just be the length of this line segment. That's the x coordinate of the point, right? So if you have a point on the graph, x comma y, in this problem, it depends on the problem. Here, x is r. X is the radius of the circle. Here, y is equal to the height. The height of the point tells you the height of the cylinder. The x coordinate of the point is giving you the radius. Does that make sense? And so when you talk about a cylinder, right, cylinders can have different circumferences. They have different heights. They can have different thicknesses. And so they each are independent of each other. Okay, so the circumference is not going to tell you about the thickness, and it's not going to tell you about the height. So all three of those things exist independently. Does that make sense?
Yeah, that makes sense. Thank you.
Okay, cool. So what we're doing here is, when you found area, you used approximating rectangles to approximate the area. So when we want to approximate an area, we used rectangles whose areas added up to a space that was about the same as the area under the graph. And then we applied a limiting process to the sum of the areas of those rectangles in such a way that the limit of the sum of the areas was the actual area. And that limit is translated into a definite integral. Okay, so the definite integral is the limit of the sum of areas of approximating rectangles. And that limit of sums approaches the actual area under the graph. Here, it's very similar, but instead of areas of rectangles, we're using volumes of cylindrical shells. And so our actual three-dimensional space that you give rotating that region around the y-axis, that actual three-dimensional region has an actual definite volume, one value. And to do that, and to find the actual value, we approximate the three-dimensional object using approximating cylinders. We break up the three-dimensional object into cylinders, not cylinders that match exactly the volume, but cylinders that very closely approximate the three-dimensional space that the object takes up. And so when we break up the object into approximating cylinders, when you add up the volumes of those approximating cylinders, it's close to the volume of the actual space. Then we apply a limiting process where the limit of the sums of the volumes of those approximating cylinders, the limit of those sums approaches the actual volume of the object. And that limit process is described by a definite integral. And so when you calculate a definite integral, in this case, you're calculating the limit of a sum of approximating the sum of the volumes of approximating cylinders. And that's how you're getting the actual volume. Okay? All right. So what I'm going to do so that's the picture. And so here, what this equation is saying is that the actual volume in this example is obtained by considering the approximating cylinders, 2 pi x f of x, so the radius is x and the height is f of x, like I drew in that picture. And then you keep approximating the volume better and better by using more approximating cylinders and making the thickness smaller and smaller. So the thickness of every cylinder is approximating cylinder is getting smaller and smaller. And you're adding up more and more of them because they're getting smaller and smaller in depth. So you need more of them to approximate the space. But when you take the limit of these approximations where the thickness is approaching 0, then you're actually approaching the actual volume. And so that limit of sums is this definite integral. So this definite integral tells you the exact volume of the object we create by taking a graph, y equals f of x, right? And a region bounded by that graph in the x-axis and rotating it around the y-axis. We get a three-dimensional object, and its volume is determined to be exactly equal to the definite integral from a to b of 2 pi x f of x dx. So when you calculate that definite integral, you're finding the volume in this situation using approximating cylinders. Okay, so I said a lot. So let's do an example. Okay. Example 1. Find the volume of the solid obtained by rotating about the y-axis, like we were talking about, the region bounded by y equals 2x squared minus x cubed, the exact example, and y equals 0. Okay? So now let's find that volume that the picture illustrated. Okay, so to remind you one more time, this is our region. You have this region here in the blue, right, in the x-axis, and you rotate it around the y-axis, and you get this thing. This is a picture of an approximating cylinder, but we're actually taking sums of them, and then the limit of those sums, which is a definite integral, and then that will give us the answer. So the solution is that the volume of that region is equal to the definite integral from a to b of this thing, right? So in between, I'm going to put this thing here. Okay, so it's equal to that. Now a is 0 and b is 2. And that's because the graph crosses the x-axis at x equals 0 and x equals 2. This is a and this is b. Okay, so this equals a and this equals b. Okay? And then f of x is 2x squared minus x cubed, and the x is just the x coordinate. Okay. So this is equal to 2 pi x, f of x, which is 2x squared minus x cubed dx. Okay, and then when you calculate that definite integral, you get the answer. Okay, so first you move 2 pi out, and then you evaluate the definite integral. So you have an antiderivative x cubed minus x to the 4th over 4. Okay, and so that's an antiderivative. Oh, sorry. Wait. Oh. Never mind. All right, I'm gonna just, you have to multiply by the x here. So you have from 0 to, and then it's x times that. So you have 2x cubed minus x to the 4th dx. Okay. All right. So just don't forget things. So you have the x times that. You get this. Now calculate the differential. Okay. So this is equal to 2 pi times now an antiderivative of that. So you get x to the 4th over 2, because it's x to the 4th over 4. 2 over 4 is 1/2. This is minus x to the 5th over 5. And then this is evaluated from 0 to 2. Okay, and so now you evaluate that, and so you get 2 pi times one thing minus another thing using fundamental theorem of calculus. So when you plug in 2, you get 16 over 2, which is 8, minus 2 to the 5th, which is 32 over 5, which is 32 over 5. And then when you plug in 0, you get 0 minus 0. Okay, so those are the calculations of that. And then, okay, so this is equal to 2 pi times, now 8 minus 32 over 5 is 40 over 5 minus 32 over 5, so that's 8/5 minus 0. So that's 2 pi times 8/5, so that's 16/5 pi. Okay, that's the answer. Okay, so these are just calculations here. The new thing of the problem is just saying that the volume is equal to this. Okay, once you get that the volume is equal to that, you reduce the problem to calculating a definite integral, which we've done before. Okay, so that's example 1. So
could you explain how you got 2 as your B?
Sure. So I'm just going to write this one thing and then answer that. Okay, so I'm just going to write the new information, the new thing in this problem is expressing the volume as a definite integral. The rest of it is just calculating it, which is old stuff. Okay, and so now let me go here. So the B is 2 because the region you originally think of, this region here, it's the region bounded by the x-axis and y equals 2x squared minus x cubed. This is the region that you're rotating about the y-axis. And so that region starts at x equals 0 and ends at x equals 2. That makes sense?
Wait, why does it end at x equals 2?
Okay, good question. So what's happening here is we're taking the entire volume, the original object, right? We're taking that and we're approximating with approximating cylinders. Those approximating cylinders have a thickness to it, this delta x here. But those delta x's are partitioning, separating the x values that make up our space. So this space that we're talking about starts here and ends here, right? The x values range from here to here, and then we rotate that. We rotate this thing, just like we rotate everything. We're rotating all of this around. And so before the rotation, if we were to think of this space and rotate it, we would separate this into, we'd be making different approximating rectangles. So that's one approximating rectangle. Here's another one. Here's another one. Here's another one. Here's another one, right? So you would separate this entire space into approximating rectangles. So you see how if we were finding the area, we would use these approximating rectangles maybe?
Yeah.
And then if we take each approximating rectangle and rotate it around the y-axis, do you see that those cylinders, the volumes of those cylinders added up would be breaking apart the actual volume? Do you see that?
Yeah.
Do you see that we don't need more approximating cylinders? We don't need more approximating rectangles to rotate. We start at a equals 0 and we end it at b equals 2. Do you see that?
No, I get that. I just don't get why the number 2 specifically.
Because 2 is the x intercept of y equals 2x squared minus x cubed.
Oh, okay, fine.
Now it makes sense?
Yeah.
Okay, good. Okay, so it was a simpler question than what I thought. Yeah, it's just 2 because 0 and 2 are the x intercepts of y equals 2x squared minus x cubed. On a higher level, why do we care about the x intercepts, right? We care about the x intercepts because the region we're rotating starts at x equals 0 and ends at x equals 2. And to approximate the area, we approximate using approximating rectangles, those red things. And then when we rotate the two-dimensional region around, we get a three-dimensional region. And just like we approximate the two-dimensional space with approximating rectangles, we approximate the three-dimensional space with the approximating cylinders that we get by taking those approximating rectangles and rotating them around, getting an approximating cylinder for each of them. And so this approximation method is only using rectangles whose thickness starts at a equals 0 and ends at b equals 2. Okay, and so that's the closer to the reason for why it starts at 0 and ends at 2. Okay, so then, okay, that's example 1. Okay, so example 2. And so what I'm saying is that these type of problems you break down into maybe so far 2 steps. Step 1, find a definite integral that represents your volume. Step 2, calculate it. Step 1, find the definite integral that represents your volume. Step 2, calculate that definite integral. Then you're done. You have the volume. Okay, so example 2. Find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. Okay. So for this, it's always helpful to draw a picture of these kind of examples, especially if you're just learning it. Okay, so y equals x squared, y equals x cubed. And if you don't draw a picture, you're probably still visualizing in your head what's happening. So y equals x squared and x cubed. So y equals x squared looks kind of like this. And y equals x cubed will look like something like this. Okay, and their intersection points are here and here. Okay, so this
Professor,
intersection point,
where are you getting x cubed from?
is that what the what? Oh, y equals x and y equals x squared. Okay, I bet. Okay. Oops. Okay. Okay, so y equals x. Okay, this is y equals x. Okay, so you have y equals x squared and y equals x. Okay, so you have y equals x squared in the blue graph, you have y equals x, the red graph, and you want to find the area bounded by those two regions. And so the space you want to find is, so you have this space here, bounded by y equals x squared and y equals x in purple there. And so then you rotate that about the y-axis. So you rotate this about the y-axis. Okay, so when you rotate this about the y-axis, you would then take this point to itself, and you would take this point and you would bring this here. And so you would rotate this point like this, that point would stay where it is. And so you see how we get kind of this, like this cone here. That's your three-dimensional space. Oh, wait, no, my bad. Okay, so then this line here would be reflected to that line. So we're rotating the purple part. So you're getting this thing here. Okay, so if you were to take a point on this line and rotate around, you get something like that. So you're rotating that purple region around. It's not the whole thing. It's just this purple part, and you're rotating it around. Okay, but this is very similar to the other example. The only difference is that the height is no longer determined by the height of a graph. The height is determined by a difference of two graphs. So here we have that the approximating rectangle to approximate the purple region is a vertical rectangle like this. And so we're going to rotate that rectangle around. And when you rotate that rectangle around, you're going to get an approximating cylinder kind of like that. Okay. And so the height of that approximating cylinder H, right? The height of the cylinder is equal to the difference of the top function and the bottom function. So this red graph is the top function. See how red is at the top? And the blue one is at the bottom. Okay, so the red graph is on top and the blue one is at the bottom. And so that means that the top graph is x, and you're subtracting the y value, which is x, minus the y value of the bottom graph, which is x squared. Okay, so h is equal to x minus x squared. And these x values are between 0 and 1. And so you might think x squared should be larger than x, but actually between 0 and 1, x is larger than x squared. Like for instance, 1/2 is larger than 1/2 squared. So x minus x squared is not negative here. Okay, so the height of this approximating rectangle for the purple region is x minus x squared. The radius of this cylinder, the radius is the x coordinate of that point. Okay, so the radius is equal to x. Okay, so the volume of the cylindrical shell is 2 pi x f of x.
Professor,
Yeah.
how do you know which one's the top and which one's the bottom?
But you see the purple region?
Yeah.
You see which line is at the top, the red or the blue one?
The red one. So
Right,
it's whatever is on top of what you're trying to find. You're trying to find the area of the purple one.
Exactly. So it's
Okay.
the purple region that we're rotating. So it's the top part of the purple region. You see here how blue is at the top and res at the bottom, but we're not rotating here. We're rotating here.
All right, thank you.
Make sense? Okay, so it made sense. Good. Okay, so we have 2 pi x f of x delta x. That's the area. That's the volume of the cylindrical shell. Just happened. Screen. Okay. These controls. Okay, so the volume of the cylindrical shell is equal to 2 pi x f of x dx. And so, good. Okay, so here, solution to find. Okay, so step 1, find the definite integral representing the volume, the exact volume. Step 2, evaluate that definite integral. Okay, so these are the 2 steps we're going to use to solve for example 2. So now let's do it. Okay, so the volume is equal to the definite integral from 0 to 1 of 2 pi x f of x dx, and that's equal to the definite integral from 0 to 1 of 2 pi x. Now f of x, here f of x, is equal to the height of the red graph minus the height of the blue graph. And in the picture, that was equal to x minus x squared. Okay, so the f of x is x minus x squared, and then dx. And so then you calculate, that's step 1. Okay, so step 1 is done. Step 1 done. Okay, and so now to continue, we're going to evaluate that definite integral, and that's step 2. So it's 2 pi times the definite integral from 0 to 1 of x squared minus x cubed, because you're multiplying x times x minus x squared dx. And then that's equal to 2 pi times, now an antiderivative is x cubed over 3 minus x to the 4th over 4, and you're evaluating it from 0 to 1. Okay, and so then that's equal to 2 pi. That's equal to 2 pi times right, the difference between these 2 values. So when you plug in 1, you get 1/3 minus 1/4. And when you plug in 0, you get 0 minus 0. And so then you calculate that. And so you get 2 pi times 1/3 minus 1/4, which is 4/12 minus 3/12, which is 1/12. And so this is equal to pi over 6. Oops. To pi over 6. Okay. And that's the answer. So now the problem's done. Okay. So
Could
that
you
is
explain how to get the radius again?
sure. Okay, so the radius here, right, is x, right? And the general formula for this type of a problem here tells you can use x as the radius. It says the volume of the solid in the figure on whiteboard obtained by rotating about the y-axis, the region under the curve y equals f of x from a to b is this, right? And so okay, so here in the problem, the x is the radius of this cylinder. So when you have an approximating cylinder, right, you have its thickness, which is delta x, which you use the dx for. The radius here is there, and then that's the height, right? So you have 2 pi x f of x. You have 2 pi x, 2 pi r for the circumference, and then times the height times the thickness, right? So the radius, though, the radius here is, this is going up over the y-axis. The y-axis is going through this point in the problem, right? And so the point on the graph is here. That's this point. And so the radius is just how far away this point is from the y-axis. That's the x-coordinate of that point. And so when we're integrating, we have 2 pi x. That represents 2 pi r. And f of x is the height. And in this example, the height, h, was x minus x squared. And it's delta x. Does that make sense? Okay. The way we constructed the problem was that the radius of this cylindrical shell was the same as the x coordinate, as if it was equal to x. If we constructed a different type of problem, it wouldn't have to, the radius wouldn't be x. But because we're taking a region bounded by a graph in the x-axis and rotating it about the y-axis, the radius is the x, always x in that example. Does that make sense? A little?
A little bit, but let's move on. Yeah, I don't think I'm gonna get it now.
Okay, yeah, it takes a little time to get. I think the best way to understand this, though, is to go the quick route and show you the formula for computing this volume in this specific example, and then calculating a volume, getting the answer right, and then maybe working backwards and saying, okay, how did I get this problem right? Does that make sense? So use the formula, get the volume for the specific example correct by getting the right formula down, and then working backwards is, okay, what is the thing I'm writing down? What is that saying? Does that make sense? So this is a tough thing for students to get. So going by the formula is sometimes good, because the thing you're writing, hopefully the thing you're writing on the page from the formula is right. Instead of trying to figure out something you wrote down that's wrong, if you're using the formula correctly, you're looking at the formula you wrote correctly and you're saying, okay, what does that mean, right? So I want you to be thinking about the right thing on the page, not the wrong thing. So this is the formula. And then y is x, the radius, y is f of x, the height, y is the difference of the two values, the new height. Okay. Okay. That's example 2 in that. Okay, so next we're going to go to 7.4, which is arc length. Okay, so and so for 7.4 arc length, we want to compute the length of an arc, right? So the natural question that you ask in this section is, what is the length? What do you mean by the length of a curve? Okay, so what do you mean by the length of a curve, right? So the idea of the length of a curve is that, let's say, without even having an x and y axis, let's just say you were looking at something like this, right? And somebody asks you, how long is that? That'd be weird, right? How do you measure that? If it was a straight line, you could use a ruler, and you would put the ruler next to the straight line, and you'd be like, okay, it's 8 inches, right? But if somebody gives you this curve thing, how do you put a ruler up to it, right? It's not straight. It's moving around. And somewhat intuitive idea is that, okay, let's say it was a rope, right? And so the rope was, in a sense, moving around. You could straighten it out, right? You could straighten it out and then say, okay, let me just measure it after you straighten it out, right? So it can make sense that this thing should have a definite length, right? And so it has a length, and you can compute it, right? But in math, you can't pick up the objects, right? If you have a curve on the XY plane, you can't straighten it out, right? It's not like a rope in real life that you can straighten out and then put a ruler next to it. So in calculus, we have a method for calculating the length, not by changing the object, by keeping the curve exactly the way it is, you can calculate its length, okay, which is kind of interesting. It's pretty cool. Here is the definition of arc length, of the arc length formula. Okay, so definition, not definition, sorry. Arc length formula, it's called. Okay, so the arc length formula will give you the exact length of a curve without straightening it out. Okay, so if f' prime is continuous on the finite closed interval a comma b, then the length of the curve y equals f of x from y equals f of x for a less or equal to x less or equal to b is, and that length capital L is equal to the definite integral from a to b of the square roots of 1 plus f prime of x squared dx. Okay, the square root is not in the dx. So this is the formula for calculating the length of a curve. And so, okay, so if f prime is continuous on the finite closed interval a comma b, then the length of the curve y equals f of x from a to b is equal to that. Okay. Okay, so using Leibniz notation, you can also write the equation, the above equation, as, and so this is usually the way I would write it. Instead of writing it exactly like that, it's almost the same. You would just replace the f prime of x dx with dy dx. Okay, and so your formula would look like that. Okay, I'm going to keep the bracket there just so you can see the correspondence between f prime of x and dy dx. Okay, so that's the formula. And so the idea is that you're just, when you have, so that was just to write a really weird looking, let me simplify a little bit by drawing this. So let's say you have a curve like that, right? From A to B. You want to find the length of that curve, not the graph, not the area under the graph, but that curve, the length of that curve. You would then, in a sense, you would partition the interval from A to B, and then for each of those points on the x-axis, you would have a corresponding point on the graph, which would be the height of the graph at that point. Then, when you take these points, you'll connect them by straight line segments. Okay, so if you partition the x-axis from A to B, and you take the height of the graph at each of these dash points, right? Then connect these adjacent points with line segments. And do you see that if you were to find the sum of the lengths of these line segments of points on the curve, that this would be an approximation to the actual length, right? And so you just keep taking partitions of the finite closed interval a comma b, where the largest interval gets smaller and smaller. So they all get smaller and smaller. And so you're taking more and more points and finding their heights and connecting them by connecting adjacent points with line segments. So these sum of lengths of line segments is approximating, each is approximating the actual length, and the limit of them is the actual length. Okay, so the definition I wrote down is the limit of the sum of the lengths of these line segments. Okay, so each sum of line segments, each sum of lengths of line segments is getting closer to the actual length. And so the limit of the sum of those line segments, the limit of the sum of the lengths of those line segments is the actual length of the curve. And that limit of the sum of the lengths of those line segments is a definite integral, as I wrote down in Word. That definite integral is the limit of the sum of the lengths of those line segments. Okay, and so you just use that and you get the answer. So this is example 1. Find the length of the arc of the semi-cubical parabola y squared equals x cubed. Okay, you're just finding the length of a curve with a weird name. Okay, so it's called the semi-cubical parabola. Okay, so find the length of the arc of the graph of y squared equals x cubed between the points 1, 1 and 4, 8. Okay, so you have your graphing calculators. You can graph this using a parameterized curve, right? So in your calculator, you can use x and y as functions of t, and you can parameterize this curve, and you can express, you can draw the graph of this on your calculator using a parameterized curve. Like for instance, solution. Okay, if you wanted to graph this on your graphing calculator, you could draw the graph of a parameterized curve by doing the following. Okay, x, you can write x as a function of t, right? And x could be t cubed, and then y could be a function of t also, and y of t could be t squared. So if you express x and y as a function of t, if you wanted to graph y squared equals x cubed, x of t could be t cubed, and y of t is t squared. Then y squared is equal to, oh, no, wait, my bad. Sorry, let me fix that. X of t is just t. And I don't know, I think I did get it. If you cube t, no, if x of t is t, then, okay, it's t to 3/2. All right, that's a parameter. If x is t, then y squared equals t cubed. So y would equal t to the 3/2, right? So then y would equal x to the 3/2. Y would equal x to the 3/2. And then that would be, or you just graph y equals x to 3/2, I guess. Okay. Okay, but anyway, you have the graph, and I'm going to draw the graph here. So now here's the x-axis and y-axis. Okay, and so now you have the point 4, 8. You have the point 1, 1. You have y squared equals x cubed. That's the graph. And so we're looking at the part, the graph has a part above the x-axis and below. We're only looking at the part between these 2 points. So we only care about this part. We want to know the length of this part connecting those 2 points on the curve. Okay? And so the question is, what is the length of that? So keep in mind, we're going from x equals 1 to x equals 4. Okay? That's alluded to from the points, right? It's going from x equals 1 to x equals 4. Okay. So for the top half of the curve, we have that y is equal to x to the 3/2. And that dy dx, which is the derivative of that, is equal to 3/2 x to the 1/2. Taking the derivatives. So the arc length formula gives us that L, the length of that purple part of the line segment, is equal to the definite integral from x equals 1 to x equals 4 of the square root of 1 plus the y dx squared using Leibniz notation dx, and that's equal to the definite integral from 1 to 4 of the square root of 1 plus, well, this is dy dx right here. So that's dy dx. There we go. Squared dx. Okay, so it's 1 plus dy dx squared dx. And then you just calculate it. And so then this is equal to this definite integral, where 3/2 times x to 1/2 squared, that's 9/4 x. So when you square that, you'll get 9/4 x. Okay, so now you want to integrate that. So step 1 is done. Right, expressing, just like for finding volumes, the first step is writing the arc length as a definite integral, and step 2 is calculating the definite integral. Okay. Okay. So we are going to break down this solution into 2 steps. Step 1, find the definite integral that represents your arc length. Step 2, calculate that definite integral. And then you're done. Okay? So you want to find a definite integral that represents your arc length in step 1. Step 2, you want to calculate that definite integral. So since step 1 is done, we're now going to go to step 2. Okay? So I'll write step 2 here. So step 2 is we now have our definite integral. L is equal to this. Okay? And now we want to calculate that definite integral. And so the goal is to calculate the above definite integral. This, but by that I mean above, I wrote it again. So the goal is to calculate the above definite integral. We are going to do that for this example using U-Substitution. So just like in different calculating integral problems, you would use a different method for each. This is just being broken down to calculating a definite integral. It could involve any method we talked about. This one uses U-Substitution. And so we're going to do that, okay? So for U-Substitution, let U equal to 9/4 x. That's because the 9/4 x is what's causing, let U equal 1. plus 9/4 x, because if you want u to be everything in the square root, that thing. And that way you're just integrating the square root of u, which you can integrate, okay? So let u equal that. Then du is equal to 9/4 dx. So we get that the length is equal to this. And that's equal to, now we have another definite integral here. And then we're now going to take the square root of 1 plus, okay, that's our original definite integral. We need to prepare it for U-substitution. So this thing is u, right? But du needs 9/4 dx. And so I'm going to multiply the outside by 9/4 and inside by 9/4 and the outside by 4/9. Okay, and so now our differential is ready to be substituted by u. So we have our definite integral, which is now moved. Okay, we'll move this whole thing down now. Step 2. That way it's next to each other. Okay, the 4/9 is still in front. So 4/9 times that, right? Now for the square root, we have the square root of 1 plus 9/4 x, that's the square root of u. And then here the 9/4 dx is du, right? So now we have the integral 4/9 times the definite integral of the square root of u du. Well, if x is 1, then u is 1 plus 9/4 x, right? So note that, so these calculations are to change the limits of integration, right? So, so x equals 1 implies x equals 1 here implies that u is equal to 1 plus 9/4 times 1, which is equal to 13/4. Okay, so then u would equal to 13/4. And so that would go there. Now, x equaling to 4 implies that u is equal to 1 plus 9/4 times 4. And that's equal to, well, the 4's cancel here. You get 1 plus 9, which is 10. And so now when x is 4, u is 10. And so now we substitute for corresponding values of u. And so this is now equal to 4/9 times definite integral from 13/4 to 10. I'm just going to write this in exponential notation. u to the 1/2 du. Okay, and so now you just need to calculate that. And that's equal to 4/9 times. We're going to have u to the 1/2, which is 2u. 3/2, 2/3. 2/3 u to the 3/2. Okay, that's an antiderivative of that. So you have 13/4 valued from 13/4 to 10. Okay, and this is equal to, you have 4/9 times now. Okay, so I'm going to actually move the 2/3 out. And then I'm just going to say you have one thing minus another thing. This thing is when you plug in 10. So you have 10 to the 3/2 minus 13/4 raised to the 3/2. Okay, and so now this is the calculation here. So you have 4/9 times 2/3, and then it's u to the 3/2 evaluated from 13/4 to 10. So it's 10 to 3/2 minus 13/4 to 3/2. And so you calculate all of that. Okay, and you have 8 over 27. Okay, so you have 8 over 27 times 10 to the 3/2 minus 13/4 to 3/2, this thing. Okay, and you could leave it like that, or this also simplifies to 1/27 times 80 root 10 minus 13 root 13. All right. And so that's the answer. That's the solution to that problem. Okay. And so now that's been calculated. Okay, next. Okay, so another formula. Okay, if a curve has the equation x equals g of y for c less than or equal to y less than or equal to d, and g prime of y is continuous, and by interchanging the roles of x and y in the previous formula, we obtain the following new formula. Okay, so that new formula is that the length is equal to depth integral from c to d of the square root of 1 plus g prime of y squared dy. And using Leibniz notation, this is equal to depth integral from c to d of the square root of 1 plus dx dy squared dy. Okay, so this is another formula. Okay, this is the arc length formula for an x for a curve defined by y, or a curve x equals g of y. Let me just show you on the whiteboard what this is saying. So here we had the length of a curve, right? But we had the length of the curve where this graph was, the graph we thought about was y equals f of x, right? We defined the curve as a function of x, where the input was an x coordinate and the height was, f of x. So our original arc length formula was for that. Instead, let's say you have a curve defined by y. Let's say you have a curve defined like this, where you're going from y equals c to y equals d. Okay, so let's say you have a curve defined from y equals c to y equals d, and this curve is x is equal to g of y. So the height of the curve is not this. The height of the curve is now this. So the height of the curve is given a y value between c and d, including c and d. What's the horizontal distance this curve is from that point on the y-axis, that red length here? That would be x, right? X would be the horizontal distance of this point. Okay, so if you input a y value, the output x is the horizontal distances, right? So if you have a curve defined this way, you can still find its length. But in this situation, the length of that curve is equal to the definite integral from c to d of the square root of 1 plus g prime of y, that derivative of that graph squared, dy. Okay, it's the same idea, except you're just switching the roles of x and y. Now x is, in a sense, the height of the graph, and the y is the input, right? And so you're just switching the roles of x and y. It's the same thing. Okay, that's all that's saying. It's the same formula. You're just switching the roles of x and y. Okay, so example 2. So example 2 says find the length of the curve of the arc of the parabola y squared equals x from 0, 0 to 1, 1. Okay, so in example 2, we're going to use that new arc length formula with this function. Okay, so that's the problem. And so we're going to go to the whiteboard again. Okay, so the graph is y squared equals x. So first let's graph y squared equals x. Here's the x-axis. Here's the y-axis. Graph we're going to put in blue. So y squared equals x. So y squared equals x looks like this. Okay, so if you input a y value, let's say like 2, let's say 2, the output would be 4, which would be x. So x is growing faster than y is, right? Y squared equals x. So this is a graph of y squared equals x, the blue. And so we want the length of the arc of the parabola from 0, 0 to 1, 1. So this is the point 0, 0. And this is the point 1, 1. And so we want the length of the arc on the curve between those 2 points. So we want the length of this arc. See that? Okay. And so we want the length of that arc. And so the length of that arc is going to be given to us by the arc length formula. So the arc length formula says that the length of that arc is equal to definite integral from 0 to 1, because the y values range from y equals 0 to y equals 1, right? So it's from y equals 0 to y equals 1 of the square root of 1 plus the derivative of y squared dy. Okay, so when we calculate that, we find the length of that arc. So let's do that on Word. Okay, so the solution is, so first let's find the definite integral representing this length. Then we will calculate it. And the problem will be solved. And then the problem is solved. Okay, so Okay, so our def integral, the length of that thing is equal to def integral. Okay, and so it's from 0 to 1 of the square roots of 1 plus g prime of y squared dy. Okay, and so that's the integral we want to solve. So note that a is equal to 0, b is equal to 1. G of y is equal to g of y is equal to x raised to the 1/2, and that's because since right. So g of y is equal. That's because y squared equals x. That's our graph. That implies that y. Oh, wait, sorry. X is equal to g of y, which is equal to y squared. Good. Okay. So x is g of y, which is y squared. So x equals y squared. That's good. And then g prime of y is just the derivative of y squared with respect to y. That's 2y. Okay. A equals 0, b equals 1, g of y, x equals g of y is y squared, and g prime of y is 2y. So that's what we need. And so this is equal to the def integral from 0 to 1 of the square root of 1 plus g prime of y squared. G prime of y is 2y. It's dy. See that? Just substitute g prime of y for 2y. And then that's equal to def integral from 0 to 1 of the square root of 1 plus 4y squared dy. And so now we want to calculate this def integral. And so here we need to use trig identities. Okay, so this is step 1 is done. Okay, we calculated the def integral. I mean, we represented the length as def integral, but now we need to calculate this using trig identities. So next, we need to find the value of this def integral. To do that, we use trigonometric substitution. Okay, so remember, we have a table for trig substitution, right? And it depends on the form of your integrand, right? So the integrand is of the form is of the form a squared plus a squared plus, instead of x squared. All right, let's use that. Right, we had a table where one of the things were of the form a squared plus x squared, right? And so here x is just a variable. That it's not necessarily the x in the problem, right? So the integrand is of the form the square root of a squared plus x squared, right? And so the table we had previously, if you just look directly at the table, then it will just tell you which substitution to use. So There we go. Okay, so the integrand is of that form. And so the table says that you use these substitutions. So when you have an integrand of this, when you have something of this form, right? We'll have an expression. You'll have a substitution, and you'll have an identity. Right? That's what the three things in the table. And so here, I'll remind you what the table said. You have x equals a tan theta. And it's for values from negative pi over 2, strictly less than theta, strictly less than pi over 2. That's the substitution. Okay. And the identity is 1 plus tan squared theta is equal to secant squared theta. Okay. So we have this expression. We want to use this substitution for that range of theta values and that identity. Okay. And so let's do that now. Okay. So so note that we are using we're using y instead of note that y in this. Note that the variable y in this problem takes the role of x from this table, right? Y is the input of our function. Y is the input of our function here, and so y is doing what this table is saying. Okay, so note we have something kind of. So note that. Note that an expression of y in this problem takes the role of x from this table. So here, instead of x squared, we have 2y in parentheses squared. Okay, so the integrand is of the form, let me put it this way, 1 squared plus 2y squared. Okay, so this is the integrand here, the square root of 1 plus 4y squared. So the integrand is of this form. Okay, the integrand is of the form square root of 1 plus 4y squared is equal to square root of 1 squared plus 2y in parentheses squared. Okay, so the substitution is going to be y is equal to 2y is going to equal to 1 tan of theta. Okay, so 2y is like the x. 2y is the thing being squared, and it's equal to 1 because a is 1. A is the 1 squared. Instead of x, it's 2y. So 2y is equal to 1 tan theta is the substitution. Or y is equal to 1/2 tan theta. Okay, so substitution is y is equal to 1/2 tan theta. Okay, so we have dy d theta is 1/2 secant squared theta. Okay, so it's a derivative of tan theta secant squared theta. So you get 1/2 secant squared theta d theta. Okay, and the square root of 1 plus 4y squared, the integrand, is equal to the square root of 1 plus, well, y is 1/2 tan theta. So y squared is 1/4 tan squared theta. So that all cancels and you get tan squared theta here. So if you take this and you square it, if you square that here, right, you get 1/4 tan squared theta. 4 times 1/4 cancels and you just get tan squared theta here. Right, so that's equal to the square root of 1 plus tan squared theta. Well, the 1 plus tan squared theta is secant squared theta. The square root of that is the absolute value of secant theta, which is secant theta. For these range of theta values, secant theta is non-negative, positive, and so its absolute value is itself. That equals secant theta. Okay, and so that means that now the length L of our depth integral, which we said was equal to this, is equal to the depth integral of, well, the square root of 1 plus 4y squared is secant theta. Right, this whole thing, the square root of 1 plus 4y squared is secant theta. dy dy is equal to that. So dy is equal to 1/2 secant squared theta d theta. So you have a 1/2 secant squared theta d theta for dy. Okay, and then when y is 0, you get theta is 0. Okay, so let me put side work. Okay, so if you have y equals 0, that will imply, well, that will imply by this formula that tan theta, so right, so we have this formula here, y equals, this is a relationship between theta and y. It says that y is equal to 1/2 tan theta. And so when y is 0, that implies that theta is 0. That implies that tan theta is 0. Tan theta is 0 for the given, remember we have, according to the table, we use this range of theta values. The only time tan theta is 0 in that range of values is when theta is 0. That implies that theta equals 0. Okay, so these are values of theta. And so when y is 0 here, theta is 0 here. When y is 1, when y equals 1, that implies that tan theta is equal to 2. Okay, and well, that implies that theta is equal to tan inverse of 2. Okay, and I'm going to call tan inverse of 2 alpha. Okay, so tan inverse of 2 I'm going to call equal to alpha. And so I'm going to say this is from 0 to alpha of that. Okay, alpha is a fixed value, tan inverse of 2. And okay. Okay, so all of this is still good. I'm just gonna put this below the side work here. Okay, so this is still what we're doing. And now this is equal to this depth integral. but we can move the 1/2 out. So this 1/2, let's move that outside of the integral. So you have 1/2 here. Instead of secant theta times secant squared theta, instead of deleting the entire integral, let's make this secant cubed theta. D theta, okay? That's 1/2 definite integral from 0 to alpha of secant cubed theta d theta. And now that's equal to, so now you calculate that definite integral. So when you calculate that definite integral, you get that this is 1/2. That's 1/2 times secant theta tan theta plus ln of the absolute value of secant theta plus tan theta evaluated from 0 to alpha. So I didn't want that there. Okay, this is where I want it. 0 to alpha. Okay, so we're valuing the whole thing in brackets from 0 to alpha. And then when you calculate that, your final answer is 1/4 times in the brackets secant theta, secant alpha, tan alpha, plus ln of the absolute value of secant alpha plus tan alpha, and that's it. Okay, and so that is the length. Okay, so you use trigonometric substitution to get this, and then you compute that, and you get it's equal to this. Okay, integration by parts. Okay, and so we can simplify this a little further. You have the tan alpha is equal to 2 by how we defined it earlier. So since tan alpha equals 2, that implies that secant squared of alpha is equal to 1 plus tan squared alpha, right? You have the trig identity, 1 plus tan squared equals secant squared. So 1 plus tan squared of this has to equal secant squared of it. But 1 plus tan squared, we have the tan alpha is 2. So tan squared alpha is 4. This is 1 plus 4, which is 5. And so that tells us then that secant alpha equals the square root of 5. So secant alpha is the square root of 5. And so here we have secant alpha is the square root of 5. And we have tan alpha is 2. So tan alpha is 2, secant alpha is the square root of 5. And so then you can say that L is equal to this, which is what we already have. And that this is then equal to 1/4 times the square root of 5 times 2. So it's 2 root 5. Plus ln of the absolute value, and secant alpha is root 5, plus tan alpha, which is 2. Okay, but you're multiplying that whole thing by 1/4. So you can simplify this further. 2 times 1/4 is 1/2. To get the square root of 5 divided by 2 plus ln of the absolute value of the square root of 5 plus 2, that divided by 4. Okay, but I didn't want the ln has to be in the numerator. Plus ln of the absolute value of the square root of 5 plus 2 divided by 4. That's what I want. Okay. Okay, so then that's the most simplified answer. And so now the problem is done. Okay, so we press forward. So next is called the arc length function. Okay, so it is useful to have a function that measures the arc length of a curve from a particular fixed starting point to any other point on the curve. And so what that means is this. If you over here, let's say, okay, so you have the x-axis, you have the y-axis. Let's say you have a curve here. So let's say this is A, this is B. So let's say we have a fixed starting point, which I'll use with this pink here. So this is our fixed starting point. So we're going to fix our starting point. And then this is going to be a function that if you take any other point, let's say you chose this point, then this function will tell you, okay, well, the function will tell you the length of the arc from your starting point to that point. Okay, and then if you choose a different point, let's say you choose this point, then the function will say, okay, well, now we're going to tell you the length of this part. Make sense? So you fix the starting point, and the function, if you input into the function any point on your curve, the output will be the length of the arc from your starting point to that point. That's the arc length function. Okay? So that's the arc length function. So the arc length function is something where this is a machine diagram representation of a function. If you input any point on the curve, the output is the length of the arc from the start point to that point. Okay? Right, so any point on the curve. So if you take any points on the curve, it'll be the length of the arc starting from your start point to that point you inputted into it. And so that is the arc length function. Okay, so your arc length function, again, the input is any point to the curve, the output is the length of the arc from your fixed starting point to that point. Okay, so now let's talk about how you get this function. So there has to be some conditions in order to do this, have this function. So if a smooth curve C has the equation y equals f of x from the initial point from the initial point oh, sorry, I jumped the gun here. If a smooth curve C has the equation y equals f of x for x values between a and b inclusive, let capital S of x be the distance along capital C from the initial point P naught of a comma f of a to the point P sub, from the point Q from x comma f of x to the point Q of x comma f of x. Then S is a function called the arc length function. Defined by the equation below. Okay, so it's defined by S of x is equal to definite integral from a to x of the square root of 1 plus f prime of t squared dt. Okay, so we're using t here. T has to be a dummy variable because x is now representing a final x coordinate, final x value. So x is being used as a limit of integration for its own reason. And so we just need the dummy variable t to represent the range of values on the x-axis, okay, that we're integrating over, okay? Here, a smooth curve C is a continuously differentiable curve, okay? Okay, so our function f of x has continuous derivative. Okay, so f prime of t is a continuous function. If the derivative of f exists, f prime of t exists, and it's continuous, okay? That's what smooth curve C means, continuous derivative. Okay, so we have this arc length formula here. In the picture, so we have initial point P naught and we have Q. So what that means is that in the previous picture here, this is P naught of A comma F of A, right? The X value of the initial point is A. Initial point P naught, the X value is A, and then F of A is the Y value of that point. The height of the graph at A is F of A, that's the Y coordinate of the point. And then the final point is any other point you choose. And so you're going to call, let's say you call Q the variable point, the point you choose arbitrarily on the curve. And so that point will have an X coordinate, and its Y coordinate will be the height of the curve at that point X, right? So here's one choice of Q of X comma F of X. If I chose this X, then Q would be the point with that X value as its X coordinate, and its Y coordinate being the corresponding height of the curve at that X value. If I chose this point instead, it would have this X value, and the Y value would be the height of the graph at that X value. Okay? Initial point P naught, the point you choose on the curve, Q, X comma F of X in green. Okay, so that's what the theorem there is referring to. Okay? Our definition is is referring to. Okay, so we have now that. Okay, and so here it's a definite from a to x. And so in the picture, a to x means a to, let's say, for this point, it would be this x value. Right? If I chose this point, we'd have an x value here. It depends on the point you choose. But then the initial point, right? Here is the initial point here. So here, that's the a, right? The initial point is, so you're integrating from a to x. So that's the curve. And this x, you'd then be integrating from here to here to find that. Okay. Okay, so you have that. And so the following equations immediately follow from the one above. Okay, so you have s of x is equal to that. So ds dx is equal to then the square root of 1 plus dy dx squared. Okay, that's just because, right, if you take the derivative of an antiderivative, they cancel, and you end up with just the integrand. Right, so the square, by integrand, the square root of that, right, you get that. F prime of t, you can just use Leibniz notation, and you get that, okay? You don't need the dummy variable anymore, because x is gone here, so you can just write it like that. Okay, so then, so this dx is that, ds is equal to this expression, dx. Okay, so those two equations immediately follow from the arc length formula, or the arc length function. And also another one, ds squared. ds, put this in parentheses, you're squaring the ds. ds squared is equal to dx squared plus dy squared. So that's from the Pythagorean Theorem. So here, if you look at a curve, if you're looking at a curve here, I guess I'll draw this whole thing. Okay, so if you have the x-axis, you have the y-axis, you have your curve. Here's A, here's B. If you were to take, let's say, this thing here, right, as part of your length, the ds would be this length here. Then the height of this triangle would be dy. The base would be dx. And so the ds squared would be, oh, so let me just, oh, that worked. Okay, so then, right, so if you take the derivative at this point, right, you get a tangent line. And so then, though, if you stop at some point, then dy is the height that the tangent line goes along a very small dx distance. And so now the length of the tangent line here, that's ds. And so by the Pythagorean theorem, you have the relationship that dx squared plus dy squared is equal to ds squared. Okay, dx squared plus dy squared is equal to ds squared. That's called symmetric form. Okay, so that comes from the Pythagorean theorem. You're using tangent lines in order to approximate the length of the curve at a point. You have an infinitesimally small dx. The hypotenuse is your ds, which is approximating the length of the curve at that point. And so that ds squared is equal to dx squared plus dy squared. Okay. So that's what that means. You won't have to worry too much about that. Okay. For it all. Okay, example 7. Find the arc length function for the curve y equals to x squared minus 1/8 ln of x So find the arc length function for that curve, taking the point P naught, 1, 1, as the starting point. Okay, so just give me another minute or two, a few more minutes, and then I can finish this section, and then we're done with chapter 7. And we're done with the material for S2. Okay, so solution. So if f of x is equal to x squared minus 1/8 ln of x, then the derivative f prime of x is equal to 2x minus 1/8 times 1 over x, right? Derivative of ln. So that's the derivative. Then get that 1 plus f prime of x squared. I'm going to put this in brackets. 1 plus that thing squared is going to equal to 1 plus this thing squared. Right? And now if you square that and expand it and combine like terms, you will get this as 1 plus 4x squared minus 1/2, well, almost combining, I'm going to combine that after, plus 1 over 64x squared. Okay, and so then you get that. And then this is equal to 4x squared plus 1/2 plus 1 over 64x squared. And that's equal to 2x plus 1 over 8x squared. Okay, so people wonder how in the world would you get that? So there's a technique to that. So I'm making the observation that this thing is equal to that thing squared. And so the trick is this, you kind of work backwards. So you kind of, if you have an expression like this, and you want to, the goal is you want to express this as a square. And so the reason you want to express that as a square is because the goal is to find the arc length function. So s of x, the arc length function, is equal to, in this problem, the definite integral from the starting point at x equals 1 to the ending point, which is at an arbitrary x that you choose, the square root of 1 plus f prime of x squared. I'm using a dummy variable here, so it's going to be t. Okay. Okay, you see, the goal is you want to find that. Now, when you do some calculations to simplify this, write this in simpler terms. Okay, so you have 1 to x. But now, what is this? This is this expression, right? So what you have is the square root of this expression dt, right? Because 1 plus f prime of t squared is equal to this, where you have a t here. Okay, so you have this expression here. So it would be nice if we could express this expression as something squared. And if we could express this thing, which is here, as something squared, then we could take the square root of something squared and we could end up with just an expression that would be easy to integrate. And the solution is that we do. We express this as this squared. And the way you kind of visualize that is that the 4x squared in the leading term, the 4x squared is equal to 2x squared. Okay? The 1 over 64x squared is equal to 1 over 8x squared. Okay, so this term is this squared. this term is that squared. And so if you get lucky, you could say that this plus this squared is equal to that. So what you do is you test it. You take the square root of this and you add to the square root of that and you square it and you see, well, if I take this plus this squared, do I get that? And so the answer is you do. If you take this thing and you square it, what that's equal is to 2x plus 1 over 8x times itself. And so you multiply this by itself when you square it. And then this is equal to, well, 2x squared, which is 4x squared, plus 1 over 8x times 1 over 8x, which is 1 over 64x squared. Now the middle terms is plus 1 over 8x times 2x is 1/4, plus the other 1 over 8x times 2x, which is also 1/4. And so when you add all this up, you get that this is equal to 4x squared plus 64x squared plus 1/4 plus 1/4, which is 1/2. And so now you see, working backwards, in order to say this equals this, first you do this and this. You write the square root of this plus the square root of that squared. And then you say, working backwards, you take that square and you say, do I get this? In this case, you do. So this equals this. And so here, this is equal to this definite integral. You have this definite integral, but you replace the integrand with that. So you replace what's in the square root with that. And so now this is equal to, this is now equal to, you have this integral here, but now the square roots go away. And so you get 2x plus 1 over 8x. It's a t though. This is a t. This is also a t. Okay, and so then you just integrate that, and then when you're done integrating that, you have your arc length function. Okay, so an antiderivative of 2t is t squared, plus an antiderivative of 1/8, 1 over 8t is 1/8 ln of the absolute value of t. Okay, and so then you evaluate this from 1.
Professor?
Yeah.
For the third to last line, what happens with the 1 plus with the 1 inside the root? What happens to that?
Oh, so it looks like I substituted f prime t squared. I have substituted 1 plus f prime here.
Oh, okay.
See that?
Yeah.
So the 1 plus this squared is substituted by that.
Okay, thank you.
Okay, so then, so now we have this is equal to, now, so don't be intimidated by the x here. You're just plugging in x as a variable. But we have a function of x as our answer. So we don't want a number as our answer. So this is x squared plus 1/8 ln of the absolute value of x minus, you plug in 1, get 1 plus, well, plus 1/8 ln of the absolute value of 1. Okay, and then this is equal to x squared plus 1/8 ln of the absolute value of x, but ln of 1 is 0, so this is minus 1. It's minus 1 plus 0, that's minus 1. And so that's your final answer. X squared plus 1/8 ln of absolute value of x plus 1, minus 1. All right, and so that's your arc length function. And just to finish this now, for instance, the arc length along the curve from the points 1, 1 to the points 3, f of 3 is, so the arc length function would say this is s of 3, because your starting point is 1, 1. That's part of your definition of s. but your ending point has an x value of 3. And so you want to know s of 3. So s of 3 would just be plugging in the x value of 3 there. So 3 squared plus 1/8 ln of the absolute value of 3 minus 1. And so you put that in your calculator, and you get that's approximately 8.1373. Okay, so now that is approximation of the length of the curve from your starting point 1, 1 to your end to this ending point you chose 3, 3. If you chose 4, 4, it'll be s of 4. And you would calculate, plug it in there, because that's your s of x. That's your s of x. So s of 3, which is just 3 squared plus 1 down absolutely 3 minus 1. Okay, and so now that is 7.4. Oh no, we still have 7.6. That's okay. Okay, so now 7.4 is done. Okay, and so before I go, I'm just going to assign more homework. If I can, wait, let me. Okay, so the next homework will be 7.4 and 7.7. So no, oh wait, but we have 7, I did 7.3. So homework is for 7.3. So homework 16 is for next class, okay? So homework 16 is due next class. Homework 16 is due next class. So that homework that covers 7.3. Okay. Okay, and don't forget that as a reminder, the second test is on April 26th. Okay, so reminder, test 2 is on April 26th at the start of class. At the start of class, only during class. Okay. Use the same Zoom link for attending a regular class as for an exam, just like the first exam. Okay, so bye everyone, and I'll see you all next week on Monday. You too.